This video is on section 5.2 notes, binomial probability distributions. So a binomial experiment is one that meets the following four requirements. The first is that the experiment consists of n identical trials. So it doesn't matter how many trials it has, but it's got multiple trials and all of the trials are conducted identically. That's important. Each trial results in one of two outcomes. These are typically referred to as success or failure. It doesn't mean positive or negative. It just means you've got one outcome or another. The probability of success remains the same in all of the trials, and the trials are independent. So this means that the outcome of one trial does not impact the outcome of another trial. One trial doesn't make it more likely or less likely that another trial is successful. So here we have some notation for binomial probability distributions. The probability of success is often going to be given to you in the problem. The fixed number of trials should often be given to you in the problem. X, a specific number of successes in the trials. You will be kind of looking at the context of the problem to determine what the random variable X stands for, so you can kind of determine what do they mean by success in this particular problem. P is the probability of success in one of the trials, and then Q is the probability of failure in one of the trials. And then these two are complements of each other, which means the probability of the successes and the probability of the failures should add up to 1. It should be 100% of the data. And then P of X is the probability of getting exactly a specific number of successes among the n trials. All right, so here's what we're going to look at first, is we're going to take a specific context. We're going to say, is it a binomial distribution? Does it follow these four requirements? Does it meet that criteria? And then if it does, let's recognize what these different values are. And in a situation where it doesn't meet that criteria, that just means that we kind of go back to section 5.1 and think about those formulas in the way that we previously learned how to do the problems. All right, so when an adult smartphone owner is randomly selected, there is a 0.05 probability that this person is cashless, which means they never carry cash, according to a U.S. bank survey of over 2003 adult smartphone users in the U.S. Find the probability that among 10 randomly selected adults, exactly 2 of them are cashless. Does this procedure result in a binomial distribution? Does it meet that 4 criteria? And then, if so, identify the values of X, N, P, and Q. So the first criteria was that the trials were identical. So here, the trials would be speaking to each of the 10 randomly selected adults. And we're going to say those are identical. They haven't given us any reason to think they aren't. They haven't said they're going to use a different questionnaire or whatever to ask them, do you have cash? Do you carry cash? They're not talking to animals sometimes and people at other times. They're not talking to adults, but then sometimes children. They said adults. So we have reason to believe that these trials are going to be identical. Are there 2 outcomes? The 2 possible outcomes here is that they are cashless, they never carry cash, or they're not cashless, meaning they sometimes carry cash. So yes, there are 2 outcomes here. Next, the probability of success remains the same. And I shorthand this. I'm just going to say probability of success this first time, but I could write P of S. Probability of success is the same. And here, they said there's a 0.05 probability that the person is cashless, and they haven't given us any reason to believe that they're going to different areas where that probability is changing. And so we're going to say, yes, the probability that the adult is cashless remains the same. And then, are the trials independent? So if we talk to one adult and they say yes, they're cashless, does it make the next person we talk to more likely or less likely to be cashless? And here we're going to say yes, those trials are independent. Talking to one person does not impact the outcome of the next person that we talk to. So if this is the case, then that means that we can go through and figure out what X and N and P and Q are. So X is going to represent the number of cashless adults. In this specific problem, they're talking to N randomly selected adults and they want exactly 2 of them to be cashless. So in this particular problem, they're going to have X equal 2. But in general, we just want to know what the X variable, the random variable, is going to stand for, and it's going to represent the number of adults that are cashless. N is the fixed number of trials. That's 10. They're talking to 10 adults. P is the probability that the person that you talk to is a cashless adult, and that was 0.05, which is 5%. And then Q is the complement of that. So we're going to do 1 minus 0.05, and that's 0.95. And that's it. That's all we have to go through. We're not doing anything with this context just yet. We're just walking through and making sure that this is appropriate to use the procedure with that we're going to go through from a binomial distribution, and that once we know it's appropriate to use that, we can recognize what these 4 things are. Okay, let's look at another context. So this one says, a meteorologist recorded the number of days of rain during a 30-day period. Find the probability that it rained less than 5 of those days. Okay, so first, do we have identical trials? Yes. It says for 30 days, so in a 30-day period, you're probably talking about your days being 24 hours each. You know, each day has a morning, afternoon, and an evening. You're probably going to look at having a same standard for did it rain, did it not rain on each of those days. There's no reason for us to believe that the trials are not going to be identical. Are there 2 outcomes? The number of days it rained is what we're looking for, so rain versus not rain. So yes, there's 2 outcomes. Next, is the probability of success the same? Is the probability that it rained on each of those days in the 30-day period going to be the same? And this is where we're going to say no. If you know anything about the weather forecast, the probability that you're going to see rain on a given day is not the same as the day before. Each day the rain forecast is slightly different, and so right here we would say no. At this stage we can say this is not a binomial probability distribution. But we can go ahead and look at the 4th item as well. Are the trials independent? This answer is not as clear-cut as the probability of rain, but I would say no for this one as well, just because rain tends to come in clusters. So we wouldn't say that if one day it rained, the next day is completely dependent on the day before. You know, it's possible for it to rain one day and not rain the next day, but often if we look at the weather, there are trends in the weather. So we'll see multiple nice days in a row or multiple rainy days in a row. So I would say that are the trials independent? We'd say no for that as well, just because we're likely to see multiple days of the same thing. All right, so now that we know how to recognize if a context for a problem is talking about a binomial distribution, now we want to look at, okay, well, what can we do with that once we have that information? So the probability of K success is a specific number of successes. So if we're thinking back to that first example we have, find the probability that among 10 randomly selected adults, exactly 2 of them are cashless. This would be the formula we would use to help us figure that out. Is this formula. So this has factorials. You can plug this into a calculator, or you can plug this into a calculator, which is going to be a little bit easier. And right down here, I want you to write down an NCK. This is how it looks when you actually plug it into your calculator. So this is the correct way to write it on paper, but this is how it's going to look. So this is saying for values of maybe you want 2 out of the 10 people to be cashless, or maybe we want 3 out of the 10 people to be cashless. We can find one specific number out of the 10 people who would be cashless. All right, so we're actually going to go through and we're going to do that exact problem. Find the probability that among 10 randomly selected adults, exactly 2 of them are cashless. All right, so let's follow the formula. So it says the probability of exactly 2 cashless adults is, and then here they say out of N trials, 10 trials, exactly 2 cashless adults. And then it's P to the K, so the probability, which is 0.05, 2 cashless adults. And then the complement, and then N minus K, so 10 minus 2. So to the adults who are the failures or the ones who would carry the cash. So notice that these 2 are complements. They're complements of the probabilities. And then these 2 numbers are kind of like complements of the trials. It's, you know, they add up to the total number of trials. So this is how we're going to write it, and then we'll plug it into our calculators. So if you're using a scientific calculator, I believe they have a button for this. If you are not sure how to plug it into your calculator and you have a different calculator than I do, then go ahead and just send me a picture of your calculator, or you can try Googling your calculator model and ask how to plug this in on Google. This is a combination. That's what you're looking for, a combination. So we're going to press the math button right here. And we're going to go over to probability. You can go to the right 3, or you can just go left 1, probability, and it's the third one down. And I gave you bad instructions because we actually have to plug in the 10 first. So this is what I was saying, is that when we plug it in on our calculator, it's going to look like 10C2. That's what it's going to look like when we plug it in on our calculator. So type in the 10 first, hit the math button, go over to the last column, probability, number 3. So 10 NCR 2. And so now we've plugged this in. Now we can do this part, and you can do parentheses, or you can just hit the times button. It doesn't matter. And then times 0.95 to the 8. And so this is the probability that out of 10 randomly selected adults, exactly 2 of them are cashless. And so I'm going to do a little squiggly equal point. And I believe the book says that here we'll do 3 significant figures. So I'm not counting the 0, 3 significant figures here. From what I've seen of my math lab, it doesn't tell you to do significant figures, it'll just tell you how many decimal places it wants. So it'll say like 1 decimal place or 4 decimal places or whatever. All right, let's try another problem. This says, based on a Gallup poll, 5% of US adults are vegetarians. If 5 adults are randomly selected, does the procedure result in a binomial distribution? If so, identify the values of X, N, P, and Q, and then find the probability that exactly 2 of the 5 adults are vegetarians and the probability that there are fewer than 3 vegetarians. So we're going to do the whole thing here. So first, I'm looking at whether the trials are identical. The answer is yes. We're talking to adults. We're not talking to children. We're not talking to animals. So we don't have any reason to believe the trials are not identical. Do we have 2 outcomes? Yes, we have vegetarian and not vegetarian. Is the probability of success the same? They tell us that 5% of US adults are vegetarian, so the probability, if we're using that statistic, the probability of getting a vegetarian when you talk to an adult is 5%, or 0.05 probability, and so the probability of success should be the same, yes. Are the trials independent? They said randomly selected adults, so we're not going to some group of vegetarians to ask these questions. So if we ask one person they're vegetarian, does that make the next person more or less likely to be vegetarian? It does not. So here we're going to say yes, the trials are independent. The outcome of one does not impact the outcome of another. All right, so first I want to recognize what my random variable is representing. So what is considered success in this case? And it's going to be the number of vegetarian adults. The number of trials is how many adults they're going to talk to. So they're talking to 5 adults. The probability is that 5%, but we're going to write it as a decimal, so 0.05. Q is the complement of that, so 1 minus 0.05 is 0.95. Okay, so we're going to go through and use that formula again. I'm going to pull it out so I can see it. Okay, so the probability that we have exactly 2 is we're going to have 2 adults out of 5, and then we do the probability raised to the second and the complement of that probability raised to the rest of the people who were not considered successes. And we just have to plug this into our calculator. So we're going to do 5, hit the math button, times 0.05 to the 2, times 0.95 to the 3, so 0.0214. Okay, so there's a 0.0214 that if you chose 5 randomly selected adults, that exactly 2 of them would be vegetarian out of the 5. Next, it says, what is the probability that there are fewer than 3? Fewer than 3 of the adults would be vegetarian. So this is going to be multiple probabilities added together. So fewer than 3 adults would be the probability that 0 of the adults are vegetarian, plus the probability that 1 of the adults is vegetarian, plus the probability that 2 of the adults is vegetarian. Not 3, because it doesn't say 3 or less. It says fewer than 3. So what we have to do is we have to find all 3 of these probabilities and then add them together. We already know what the probability that exactly 2 of the adults are vegetarian is, but we have to find these 2 probabilities. So we're going to write them both down. We're going to say the probability out of 5 adults that 0 are vegetarian. Okay, so that's the probability that 0 are vegetarian, plus the probability that 1 is vegetarian, plus the probability that I already found that 2 are vegetarian. So now we need to add this up. Okay, so I'm going to say 5, 0, plus, and now I'm going to add the next probability, and then plus 0.0214. I have a typo in there somewhere. Let me look to find it. Oh, there it is. Okay. So, I knew that I had a typo because you can't have a probability that's more than 1. So I went back through and I found where I had actually multiplied by 5 instead of raising it to the 5th power. Okay, so my probability here is 0.999 if I'm doing 3 significant figures and then rounding. This third digit right here, the 8 rounds to a 9. So if I look at this and if I think through the problem, it makes sense. So if only 5% of US adults are vegetarians, then if I talk to a group of 5 people, probably less of them are vegetarians rather than more of them. So what's the probability that 0 of them are vegetarians, 1 of them are vegetarians, or 2 of them are vegetarians? That's probably going to be every situation. It's very unlikely that if only 5% of people are vegetarians, that of a group of 5, 4 of them are vegetarians or all 5 of them are vegetarians. That's just not very likely. So that's what this is saying here, is that if I talk to 5 people, pretty likely that 0 of them are vegetarians or only 1 or only 2. Not very likely that more of them are going to be vegetarian out of that group. All right, let's look at another problem. So this says, of all the Harry Potter books purchased, about 60% were purchased for readers 14 or older. If 12 Harry Potter fans who bought books are surveyed, find the following probabilities. Then find the mean and standard deviation of the binomial distribution. So here we don't have to check to see if it's a binomial distribution. We know from the context of the problem that it is. So we can just go through and actually calculate the different answers from here. However, I'm going to show you how to use, instead of a calculator, how to use the binomial probability distribution table to calculate these problems, because as you could see from this last one that we did, it can start to get a little cumbersome to use this formula depending on how the problem is phrased and how many probabilities you have to add together. So if we had, in this case, 12 different people that we're talking to, at least 5 of them are 14 or older. Now we're starting to add more together. If we were to add 20 pieces of data together, that would be really frustrating to have to type that formula 20 times and add all those numbers together. So I'm going to show you guys how to work with the table. So the printed version of the table I have right here, and before we even get started using the table to do some of these calculations, I just want to explain to you how the table works. So first, we have this column right here, which is the number of trials that we have. So we have on the first page, you see what I'm writing? Yeah, number of trials. So on the first page, we have for 2 trials, 3 trials, 4 trials, 5 trials. This packet only goes to 20 trials. So if you have more trials than that, you can't use this packet. All right, then this next column, this R, is if you have that many trials, how many successes do you have? So for 2 trials, you could have 0 successes, 1 success, or 2 successes. For 5 trials, you could have 0 successes, 1, 2, 3, 4, or 5 successes. So this, I'm going to put the label down here. This column right here is the number of successes you want to have. Okay? Across the top here is the probabilities, and you'll notice this is not every single probability you could have. They basically, except for the first one, go by 5s, so that's going to limit when you can use the table as well. So this table can't be used for every problem. It's a little bit limited, but in the situations where we can use the problems, it's going to be really nice to be able to have it. Okay, so we have that. Let's go ahead and start talking about this problem. So we know it's a binomial distribution. We don't have to check the 4 requirements because of that, since they said it in the problem. So what we do want to do is recognize what X, N, P, and Q are. So X, we want to know what a success is talking about, what the random variable represents. So X represents the number of book purchasers, people who bought books, who were 14 or older. Either they were 14 or older, or they weren't. Next, we want to look at how many trials we're talking about. So it says 12 people who bought books, so 12. The probability of success is 60%. So 0.60, and then the probability of failure is the complement of that. So 1 minus 0.60 is 0.40, or 40%. Okay, so it says find the probability that at least 5 of them, so we're going to say probability that X is greater than or equal to 5. The probability that at least 5 of the 12 are 14 or older. So what we have to do right now is we have to find the probability that X is 5, the probability that X is 6, the probability that X is 7, the probability that X is 8, the probability that X is 9, the probability that X is 10, the probability that X is 11, and the probability that X is 12. That's what we need to find to be able to answer this question. What's the probability that at least 5 of them are 14 or older, which is why we're not going to use the formula for this one. We're going to use the table. So what we need to do is look on the table, find where we have 12 trials and a probability of 60%. So that's the 3rd page. Oops, sorry. 12 trials, 60% is all the way over here, and then here they are. Here's the probabilities we're going to look at. Okay, so probability of 0 successes all the way down. Here's 5 successes. So we're starting here. 5 successes, 6 successes, 7 successes, 8, 9, 10, 11, and 12. So I could make, just like we did in the last set of notes in section 5.1, I could make a probability distribution. I could make a table from this. I could say if I have X number of successes, the probability of having those number of successes, and I could fill out this table, and that's what I'm actually going to do first. So that you guys can see how this relates to what we did before. Okay, so I'm going to look at my paper now, and I'm going to write down all these probabilities. So probability of 0 successes all the way to the probability of 12 successes. When the graph says 0.00 like this, it doesn't literally mean you have a probability of 0% chance of success. It just means that that probability is very, 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 very small. So there was probably some numbers past the third digit that were something other than 0. They just cut them off at the third digit, and it ended up approximating 0. So there's a number there. It's just very, very small. Okay, so there's all my probabilities, and if I want to know the probability that x is greater than or equal to 5, then I just have to start with 5 and add all of these together. So 0.101, 0.177, 0.227, 0.213, 0.142, 0.064, 0.017, 0.002, I had a typo, 0.002. And so this is approximately 0.943. And if you wanted to check your work and do all of these in the calculator and then add them all together, you absolutely could. All right, the next one says the probability of exactly 9. Probability of exactly 9. This one's a little bit easier because we can just look. The probability of exactly 9 is 0.142. The probability that less than 3. So if we're doing less than 3, then we're going to have the probability of 0, the probability of 1, the probability of 2. So for those, we're just going to add up probability of 0, 1, and 2. And if we add all of those together, we end up just getting 0.002, because these are essentially probabilities of 0. And then last, it said also to find the mean and the standard deviation of the binomial distribution. And for that, we're just going to use these formulas. And the nice thing about these is that if you have a binomial distribution, it is so much simpler to use these formulas than to use the formulas we learned in section 5.1. So you can technically use either. You can use these or the formulas in section 5.1 and get the same answer. But if you're able to use these, then let's use them, because they're a lot more simple. So I'm going to say the mean, mu, is n times p, which is 12 times 0.6, 7.2. And the standard deviation is the square root of n times p times q, which is the square root of 12 times 0.6 times 0.4, 1.7. All right, this last problem says car color preferences change over the years. Suppose that in a recent year, 10% of all cars sold were black. If 20 cars purchased that year are randomly selected, find the following probabilities. Then find the mean and the standard deviation of the binomial distribution. So since they said that this is a binomial distribution, we don't have to check the 4 requirements. We can just jump right into the problem. So the first thing I'm going to do is define my random variable. So x is going to represent the number of black cars. So a black car would be a success, a non-black car would be a failure in this case. The number of trials that we have, is 20. And then our probability of having a black car, or our probability of success, is 0.10 from that 10% number. And then the complement of that would be 1 minus 0.10, which is 0.90. Okay, so part A says the probability that at least 5 cars are black. So probability that X is greater than or equal to 5. And so in this case, that would mean the probability that exactly 5 cars are black, plus the probability that exactly 6 cars are black, plus the probability that exactly 7 cars are black. And I'm going to put a ... here so I don't have to write all of these out, all the way up to the probability that all 20 cars are black. So that would be a lot that we're adding together. Thank goodness we have the table and we don't have to use the calculator with the formulas. So I'm going to go to the very last page of the table. So here's where we have 20 trials. The third column in is where we have the probability of 0.10. And so I'm going to come down here and we're going to look at the probability that X is greater than or equal to 5, which starts right here. So these are the numbers that I'm going to be adding together. So I have 0.032, 0.009, 0.002, and then all the rest of them are basically a 0 probability, but they're slightly more than 0. They're just approximating 0 because we cut off some decimals that were past that third digit. So I'm just going to say plus 0 right here. So 0.043 probability. Or 4.3% if you like to think in terms of percentages. So 0.043 probability. So next, find the probability that at most 6 cars are black. So the probability that at most 6 cars, so that would be less than or equal to 6. So this is 0 cars, 1 car is black, 2 cars could be black, all the way up to exactly 6, but no more than that. So from 0 cars all the way up to 6. So I've got my 20 trials, 0.10 probability, and I'm going to be going from here to 6. So 0.122, 0.270, 0.285, 0.190, 0.090, 0.032, 0.009, 0.998. Okay, C says more than 4 cars are black. More than 4 cars would be like 5 cars, 6 cars, 7 cars, 8 cars. We actually did that already. This is exactly the same as part A. More than 4 cars is the same as saying that the probability is greater than or equal to 5. So we found that number already. Probability that exactly 4 cars are black. So this is just only 4. So we can do 0.10 probability, 20 trials, that exactly 4 is 0.090. The probability that between 3 and 5 cars inclusive are black. So the probability that between 3 and 5 cars are black, when it says inclusive, it means including 3, including 5. So this would be the probability of 3 cars, the probability of 4 cars, and the probability of 5 cars. That 3, 4, or 5 out of 20 are black. So here, 3 is 0.190, 4 is 0.090, 5 is 0.032, So that's 0.312. And then the last one is the probability that more than 15 cars are not black. More than 15 are not black. And we don't have the data for this. We have the data for black. So more than 15 are not black. That means that if we're talking about black cars, we're talking about 5 of them, because altogether there should be 20 trials. So more than 15 are not black. That would mean that less than 5 are black. More than 15 are not black. That means that less than 5 are black. So we're kind of looking at like the opposite phrasing. So this would be 0, 1, 2, 3, and 4. .957. Okay, and then it also said to find the mean and the standard deviation. So the mean is n times p, which is 20 times 0.10, so that would be 2. And the standard deviation is the square root of n times p times q. So 20 times 0.10 times 0.90. .3.